we left off last time, there were like maybe some examples of computing some domains, and maybe some examples of graphing via transformation that we didn't address. Should we address these? Cool. Which one should we address first? I guess the domain questions, A and C we can do. Interest in A? Cool. Maybe I'll just write this much. If you wanted to find the domain of this function, what inequality should you write down? What types of things are you allowed to see in a log? Things greater than 0. So whatever's inside of that log needs to be greater than 0. And that looks like an inequality you know how to solve, so maybe I'll just leave it there. Figure out where it's equal to 0 and then check some sample point, or think to yourself, well, it's just a parabola, it's downward opening, so I can just draw a picture and read it off that way. Next one, C. What inequality do you need to solve for that? Here's what you need to solve. Absolute x strictly bigger than 0. And absolute value is like more complicated than linear, so if you don't see anything more obvious to do, the thing you should try is figure out where it's equal to 0. Where is absolute value equal to 0? Just 0. So step 1, solve absolute x equal to 0. The only number whose absolute value of 0 is 0. So x is 0. And now let's think about some sample points. If I plug in a negative number, is the absolute value positive or negative? Positive, so I should include everything less than 0. What about anything bigger than 0? Also include? Cool. So it looks like 0 is the only thing left to check. Is x equals 0 in the domain of this function? No, because I need absolute value to be strictly bigger than 0. So it looks like the domain all right, we talked through it, maybe we didn't write anything. It looks like the domain is all numbers but 0. Oh, I guess if you like intervals negative infinity to 0 together with 0 to infinity. That feel pretty good? I don't know, maybe one last thing. If you wanted to check if these are correct, what's some stuff you could do? Yeah, say it louder. Yeah, you could graph these things using a machine. The machine's always a little bit dicey in that maybe it won't tell you like exactly where the endpoints are if they're not at some like obvious number. But you know, you could discover the actual endpoint that you find, get a decimal approximation, see if it's close to what the calculator gives you. And I don't know. I guess let's just do it. Log base 1/2 of absolute value of x. That look like it has something bad happening at 0? But nothing bad happening anywhere else? Cool. I think the domain's everything but 0. Oh, maybe here's one last question. The stuff we did to compute this domain, did it matter at all what the base is? If you change the base, we'll see that on the next page why that's true. You change the base, you don't change the domain. Should we talk about graphing via transformations with logarithms? Is there a demand for that bottommost example? Oh, okay, cool. But I won't. Let's move on. So, we've seen logarithms are powerful in that they let you solve exponential equations. They're also kind of complicated and can be difficult to get a firm grasp on what the log of a thing is. But they do behave, they have some really nice algebraic laws. And if anything, these algebraic laws are like why logs were originally invented. So let's write down these things that I'll call logarithm laws. We'll use them. And then I think there'll be some time after we explore those ideas. Then we'll talk about why they're true. So let's write down some logarithm laws. I guess the first couple you already know. What's the log base b of 1? Say louder. 0? Because you ask yourself, oh, what power of b is 1? b to the 0 is 1. That's what logs measure. What's the log base b of b? 1. If you take the log base a thing of that same thing, you always get 1 back. The remaining ones are ones that we haven't seen before. And you can think of these as saying that logs like downgrade these algebraic manipulations. So the log of a product, if you take the log base b of x times y, that turns out to be the same thing as the log base b of x plus the log base b of y. So if you ever see two numbers inside of a log and they're multiplied, you can split it up into two separate logs with the sum. And here's one reason that, like, this is really the reason that logs were originally studied. Multiplication is kind of hard to do. Addition is much easier to do. In that, if you're living, say, 60 years ago, and you don't have access to handheld electronics, but you do have a slide rule. Anyone here ever used a slide rule? I think the time has come that that question will not be answered with a yes ever again. Has anyone here ever seen a slide rule? Know what a slide rule is? Oh, okay, yeah. It's like you have some bars, and you just, if you want to add things together, you push one of them over enough to do the addition, and then you see where something else lands, and that's the result of addition. So it just mechanically does addition. So if you have two big numbers you want to multiply together, what do? You grab your big book of log tables, you look up the logarithm for these two numbers, you use your slide rule to add them together, then you have, now you know what the sum of their logs are, so you know the log of the product. If you want to know the product, you grab another book, which is an inverse log table. You figure out what the inverse log of that product is, and hey, you've just done multiplication without having to directly multiply. And if you have some like really big numbers that you want to multiply accurately, that's faster than doing it by hand. That's not what the computer does, though. So log downgrades multiplication to addition. So what do you think of downgrades division to? Subtraction. And we'll see that is literally true. This is the same thing as the log base b x minus log base b y. And again, like, you can see why that's useful. Division is hard to do by hand. If I give you two like 30-digit numbers and ask you to divide one by the other, it's kind of annoying if you don't have access to a machine. But if I give you a 30-digit number and another 30-digit number and ask you to subtract them, it's easier. You have to do like something 30 times, but that's easy. Or if you have a slide rule, you can use the slide rule to do subtraction. And then you just play the same game translating from division to subtraction via log, and then back to division by inverse log. Inverse log, by the way, what is the inverse function to a logarithmic function? What are logs an inverse function for? Exponentials. So inverse functions to logs are now exponents. So, right, like the fancy word that these lookup tables have that like engineers from a half century ago would use are called inverse log tables. But really they're just exponential tables. They're just a book that's full of values that logs and exponentials take. Neato. Folks feeling good? So, multiplication downgrades to addition. Division downgrades to subtraction. What should exponentiation downgrade to? Say louder. Kind of like addition. So exponentiation is like iterated multiplication already. So this should be downgraded to iterated addition, which is another word for multiplication. So let's write that down. If you see an exponent inside of a log, you can rewrite that as the log, same base, same input, multiplied by y. Feel pretty good? Another one that we saw use of last time was the change of base formula. In that if you have a calculator that can only work with respect to one base, that doesn't actually need to hold you back. You can do logarithms with any base if you understand one base and can do division. The log base a of x, if a is a base you don't like, is the same thing as the log with respect to any base of x divided by log with respect to that same base of a. So if you see a log that you don't like the base of, you don't need to use that base. You just need to introduce in division. The same thing is true for exponentials. If you see a base in an exponent that you don't like, you don't have to have that exponent. You can change to a different exponent. A to the x is the same thing as a to the x times, oh, nope, I changed the base. Some other base, x times log base b of a. And I want to do a Desmos demo to convince you that something like this is true. So let's think about what this would mean. This means that if you want to think about log base a of x, you can think about log base b of x. You can do it by just dividing log base b of x by this thing in pink. And that thing that I just underlined in pink, are there any x's in it? So it's just a constant. So to get log base a of x from log base b of x, you divide by a constant. What does that do to a graph? Let me ask this question. So if you take you know what the graph of that looks like? And you get the graph of y equals that. So that would be like all the y values get divided by a number. So it would be like a vertical compression, or a vertical stretch if you're dividing by like a fifth or something. So all the different logs, according to this, should have the same graph. They should just either be stretched or compressed vertically. Shall we see if that's true? All right. Let's pull up Desmos. Let's pick a preferred base. Give me your favorite base to have for a logarithm. 10. Not a bad choice. So there's the log base 10 of x. Now, let's let some parameter b vary. Let's set it to be 2 by default. I guess we'll let it run from like 0.1 to like 40. So that's just some constant that we'll let move around. Let's get to the log base b of x. And let's just see that. Does the green graph look like the red graph but either vertically stretched or compressed? Yeah. And let's see what happens as that parameter b changes. As the b gets bigger, does it get squished down, compressed vertically? All right. And, oh, I missed it when the b was going the other way. And as it gets big, it gets big. And eventually, I guess it reflects over the x-axis. Does that make sense that it would do that? What's the log of 0.6? Positive or negative? What sort of power do I need to raise 10 to get 0.6? Negative. Because 10 to a positive power will be at least 1. So that log is negative, which is why it reflects. That feel pretty good? So all logs have the same graph, except vertically stretched, maybe vertically flipped. We also have this rule for exponentials. So that means that any exponential is the same as your favorite exponential with that x multiplied by a number. What happens to the graph of a function when you multiply the input by a number? How would you get the graph of that? Sorry, this rule is absolutely terrible. And you're just absolutely off the seat because of it. I guess they're open seats. F of 2x, how do you get that? I heard whispers that seemed promising. Stretch the graph. Except it's inside the parentheses, so you do the opposite. So that's a compression. If it were 1/2, then you would stretch. Let's see if that happens with this. So a to the x should just be a stretch or a compression of b to the x. So let's see that happen. What's your favorite base for an exponential? 2. Interesting that you didn't say 10, because that was your previous one. So there's the graph of 2 to the x. Now let's look at b to the x. And again, we'll let this b vary. Do these all look like horizontal compressions of that? Yeah, except when the base b is less than 2, then it's getting stretched out. That feel good? Nice. So all exponentials are basically the same. All logarithms are basically the same. Kind of. Cool. We feel pretty good about this? Let's use these laws to do some things. So here's the first thing I want to do. We can evaluate things that we couldn't before using these rules, which I guess makes sense because the algebraic rules for exponentials you can use to evaluate some exponentials that you couldn't before, or at least couldn't directly. Let's try to compute that first one. Log base 3 of 2 plus log base 3 of 1.5. Which of those rules seems handy right now? Yeah, I see 2 different logs in a sum. I can combine those into a single log. Log base 3 of 2 plus log base 3 of 1.5 is the same as log base 3 of 2 times 1.5. And now let's just see what happens. What's 2 times 1.5? Say louder. 3. That is log base 3 of 3. And what is the log base 3 of 3? 1. Log base anything of that same anything is always 1. Cool. Feel pretty good? You think you could take a minute and do the one I just underlined in purple? Sorry, I said it as a question when I meant it as a demand. Compute that one. Check what you get with those around you. All right, I think I see some positive indicators. What are we getting? Like you're also a 1? Cool. Should I talk through it? Groovy. So there's a powerful thing. Logarithm laws let you turn things that you couldn't compute directly into things you can. They also let you solve some equations. Because a lot of these rules let you take 2 different logs and combine them into a single log. And once you have a single log, you can take advantage of log form versus exponential form. Let's see that in practice. Let's try to solve this equation. Log base 3 of x plus log base 3 of x plus 8 equals 2. And maybe here's the first move I'll propose. I see two different logs with the same base added together. Instead, I could write them as a single log with a product in the middle. Let's see what happens if you try that. Log base 3 of x multiplied by, ooh, I'm going to do something wrong. X plus 8 equals 2. What's wrong there? Yeah, the parentheses are important. All of x plus 8 needs to be multiplied by x. All right, neato. So now we have a single logarithm. All of the unknowns are inside of the argument of that log. So I think if we rewrite in exponential form, it'll become nicer looking. What do you get when you rewrite this as an exponential? Let's just read it out. What's the base? 3. So the base is still the base. What power is that base raised to? 2. Equals, and then it's just the stuff inside of the parentheses. X multiplied by x plus 8. Oh, cool. Does that look a little bit nicer than it did before? Yeah, in fact, now this is like a degree 2 polynomial equation. So we have like a strategy, right? We could FOIL out the left-hand side, get that thing that's on the right-hand side over to the left-hand side, then either factor or use the quadratic formula, whatever feels better once we see what we have. Let's try to do it. So, 3 squared is 9. So let's use that. So I think I see x squared plus 8x, because there's expanding that out, minus 9 equals 0. And let's see, in seeing that, how many people would be drawn towards the quadratic formula? How many people would want to try to factor and then see if it works? Cool. So in particular, I think basically everyone told me they have a plan. So I think I'm going to be quiet. You're going to tell me what x is. And then we'll come together because there's one last subtlety here. Unless anyone does want me to talk through solving that degree 2 polynomial. Okay. Dot, dot, dot. The other option is also completing the square. Shots fed out. All right. Once you get some x values, go ahead and compare. Together. So, what's x? If I can read lips correctly, I think that's what I saw. Excellent. So I said there's like a subtlety. That answer is incorrect. Why? Just one. I like it. Why just one? Yeah. Let's look at the domain of the original problem. I see an x in a log. X needs to be bigger than 0. So 9's out. I also need x plus 8 to be bigger than 0. So that means x needs to be bigger than -8. 9's out again. So we're seeing this like thing that I mentioned a few times. Whenever you do algebra, you can change the domain. The step where you change this to that is not long, but it makes the domain bigger. Because it could be that x and x plus 8 are both negative, but their product is positive. You know, that feels pretty good. So, after you solve any logarithmic equation, take a moment and think about domain. Is it actually in the domain of the problem? Let's do some more. Let's jump right down to this bottommost one. So I think I'm pacing myself a little bit slow. Hopefully the examples are being useful. Let's try to solve that. 2 times the log base 5 of x plus 1 minus the log base 5 of x minus 1 is equal to 2. So I think we can use a really similar strategy. It's annoying that there are multiple different logs in this thing, but they all have the same base. So I think I combine them all together to get a single logarithm. Seem like a plan? And you might say, oh, I see subtraction, so I can use like the division rule. I think you have to do something else first. Because that first thing isn't just a log, it's a log with 2 multiplied by it. Let's deal with that first. Order of operations says you do multiplication before subtraction. Let's deal with the multiplication first. What could you do with that 2? Yeah. Move it in as an exponent on top of the x plus 1. So let's do that. Log base 5 of, maybe some color coding will help now. Parentheses x plus 1 squared. Close parentheses minus log base 5 of x minus 1 equals 2. And in that step, we've definitely changed the domain. If x minus 1 is negative, then its square is going to be positive. So the domain's gotten bigger, so we just have to remember that to check that with whatever solutions we get. All right, what should we do next? Oh, sure. Yeah, let's expand that square out. So this will become log base 5 of x squared plus 2x plus 1. Did I wrote that out right? And what can I do with the minus log base 5 of x minus 1? I can divide that. Let's do that division. Divided by x minus 1. Subtraction becomes division. Equals, not 0, equals 2. Cool. All right. Now we have it down to just a single log. So what should we do next? Let's put it in exponential form. And let's go through all of the steps of doing that. What's the base? Raised to the power equals whatever it was that was on the left-hand side. Excellent. Oh, and I guess what's 5 squared? 25. Oh. All right. That look like an equation you know how to solve? Do people think they would benefit from seeing the algebra done out on that the rest of the way? Cool, then let's do that. So I see some division. I see an x in the denominator, and that's annoying. How can I get rid of that? multiply that over to the other side. Cross multiply. So, that looks like I get x squared plus 2x plus 1 equals 25x minus 1. All right, nice. That looked like an easier equation to deal with then. So life is getting better. That's good. It's always nice to reflect once you've done a few steps and see if you've improved your situation or made it worse. What should we do next? What do you mean by expand out? You're okay. I think I want to just get everything onto the same side, because then I can use the quadratic formula. And the numbers are ugly enough that I think that's just what I want to do. X squared minus 2 minus 25 is 23x. 1 plus 25 is 26 equals 0. So we're chugging along. I don't think this thing factors. So, quadratic formula says that this is equal to x equals negative b plus or minus the square root of b squared minus 4 times a times 26 all over 2. All right. And I guess at a glance that discriminant is, I think, obviously positive. 23 squared is going to be 4 times 26. So 2 solutions. Descartes' law of signs says there will be 2 or 0 positive solutions, so I think there will just be 2 positive solutions. Both of those will be positive. Let's get some decimal approximations. And using the calculator that I choose to use, you use yours. 23 plus the square root of 23 squared minus 4 times 26. Maybe I could simplify that 4 times 26 to 104 if I wanted to, but I think it's too late now. Divide by 2. So it appears one of the solutions is about 21.8. Excellent, I'm glad you agree. Or, same thing, but stick a minus sign there. Around 1.19. All right. So, what do you think? Are just both of those going to be solutions? Well, we should check anyway. There might be a domain issue. For this to make sense, x plus 1 has to be positive. So I guess that means x has to be bigger than negative 1. Both of those bigger than negative 1? So far, so good. X minus 1 has to be positive. So x has to be bigger than 1. Both of those bigger than 1? I think both of those are solutions. But you do have to do that domain check, even if you don't write anything down. Neato. How do people feel about this idea of solving equations that involve logs using these log laws? Yeah, nice. Carrying on. So, on this page, we have some explorations of what you can do with the change of base formula. And here's one, just one super straightforward. Look back at the change of base formula if you need. What is pi to the x in terms of an exponential with base 10? Pi to the x is 10 raised to what power? there's the change of base formula from the previous page. So let's try to use that. And that's true for like any a, b, and x. And I think x is just going to be x. What should I use as b? What's the base I would like to express everything in terms of? 10. Let's use b equals 10. What should I use as a? Pi. So, apparently then, pi to the x is the same thing as 10 to the x multiplied by log base 10 of pi. And you know what? Let's just do a check. Ten to the x. Oh wait, no, pi to the x was the one I wanted. Pi to the x. 10 raised to the x times log base 10 of pi. Seems to line up. Nice. So, change of base formula for exponentials seems to work. And here's another fact. So, let's use the same exploration. So, 3 to the x, let's write in terms of an exponential with base 2. So 3 to the x will be equal to 2 raised to what power?
X times log.
Yeah. So 3 to the x should be the same thing as 2 to the x times the log base 2 of 3. And let's use this handy approximation to address the rest of the question. So this will be about 2 raised to the x multiplied by 1.58. Alright, so now here are two graphs. They're not labeled at all, but you can see how they compare to each other. If I tell you that one of those is 2 to the x, and one of those is 3 to the x, which one has to be which? Let's label them as A and B. Let's think in terms of transformations. So this sure looks like 2 to the x with the x multiplied by 1.58. What does multiplying the x in a formula by 1.58 do to the graph? Say that wrong. Yeah, it sounded like there was a question mark at the end. It's definitely either compresses or stretches. And it's next to the x, so it's the opposite of what seems intuitive. So it seems like, oh yeah, all the x's should be multiplied by 1.58, but really you divide all the x's on the graph by 1.58. So does that stretch or compress? Compress. So apparently 3 to the x should be horizontally compressed from 2 to the x. All right, so use that information. Between A and B, which one is 2 to the x, which one is 3 to the x? Sounded like there was a question there. And I guess you're saying B should be 3 to the x. People agree? Anyone disagree? So y equals 3 to the x should be the same as y equals 2 to the x compressed. So you should start with y equals 2 to the x and then compress horizontally. So 3 to the x should be the one that's squeezed in closer to the y-axis. Which one of those is squeezed in closer to the y-axis? A. So A should be 3 to the x. Maybe here's another sanity check that we could use. Let's think about what happens when you plug in 1. What's 2 to the 1? What's 3 to the 1? Which one's bigger? So add an x value of 1, which I don't know, looks like there-ish. 2 to the x should be lower than 3 to the x. Which one of those two is lower at that point? B. So I think that reinforces that B is 2 to the x. All right. Let's do something similar for logs. The change of base formula for log says that the log with respect to a base you don't want to use is the same as the log with respect to a base you do like. But then divided by the log of the base you don't like. So, let's use that here. Let's express log base 3 in terms of log base 10 of x. Log base 3 of x is equal to well, I guess what should I use as A if I want to use this formula? 3. What should I use as B? 10. So let's write this side down with B equals 10, A equals 30. Log base 10 of x divided by log base 10 of 3. And you know what? Let's add this into log base 10 of 3. It's pretty close to a half. But let's get an actual decimal approximation. It's somewhere around 0.48. So that means that this is about log base 10 of x divided by 0.48. So let's follow the same strategy. One of these is log base 10 of x, one of those is log base 3 of x. Apparently log base 3 of x should look the same as log base 10 of x, but all of the y values are divided by about 1/2. What does dividing a function by 1/2 do to the graph? Do something vertical because you're dividing the whole function. It'll compress it, but because that's less than 1/2, it's going to stretch it, in fact. Like if you were dividing by 4.8, it would compress, but 4.8 is less than, so it'll stretch. So log base 3 of x should look like y equals log base 10 of x, but vertically stretched. All right. So, look at those two graphs. Maybe I'll label them again as A and B. Log base 3 of x is log base 10 of x, but vertically stretched. Which one of those is the other one vertically stretched? So one of those should be like the other, but with all the y values just about doubled. Which one of the two has bigger y values? B. This should have like all the y values double the value of log base 10 of x. So this one's log base 3. Log base 3 is the taller one. Neato. Folks feel pretty good? So you can use these change of base formulas to really understand how the different graphs of the logarithms will all compare to each other. Different logs will all just be vertically stretched or compressed from whatever your favorite log is. Different exponentials will all just be horizontally compressed or stretched from whatever your favorite exponential is. And here's one last thing that you can do with change of base formulas. I claim that you can evaluate that sucker on the nose exactly. And let's try to do that. So here's something that's annoying. I see multiple bases involved. Do you think we could rewrite all of that with just a single base? What base would you like to use? 2? 3? 10? It shouldn't matter. I'll pick one. I think 2 was the most popular, so let's use that. Let's show you everything in terms of log base 2. If you want to use log base 10, you'll get to the same answer. So let's rewrite everything in terms of log base 2. That first piece is already in terms of log base 2. Log base 2 of 3 times, let's rewrite log base 3 of 2 in terms of log base 2. So the new base is 2. So it'll be log base 2 of something divided by log base 2 of something. What goes in those parentheses? The thing on top? Because it should be whatever's in the parentheses goes in the parentheses on top. What should go on the bottom? See anything that cancels? What do you see that cancels? Log base 2 of what, though? Log base 2 of 2. Good. All right, just log base 2 can't cancel because that's like a function. So those two are the same. I don't know what log base 2 of 3 is. I mean, I guess it's like somewhere between 1 and 2 because 3 is between 2 and 2 squared. But that doesn't matter. Whatever it is, it cancels. And you wind up with just log base 2 of 2. And what is the log base 2 of 2? Did you work it out in log base 10 and get something similar? Oh, okay. Let's also... I got time. Let's imagine you didn't think to use one of those two bases. Because I saw it shouldn't matter. Let's use log base 10. Log base 2 of 3 in terms of base 10 will be log base 10 of 3 divided by log base 10 of 2. So far, so good. And what does the other one become? I'll have to do everything in terms of base 10. So it'll be log base 10 of divided by log base 10 of. What goes in the parentheses? Oh, sorry. Yeah. 2 on top, 3 on the bottom, because the thing in the parentheses becomes the thing in the parentheses. The thing in the bottom becomes the thing in the bottom. Nice. Anything cancel? Does everything cancel? Yeah. So what are you left with? Just 1. Log base 10 of 2 cancels with log base 10 of 2. Log base 10 of 3 cancels with log base 10 of 3. I find that it's sometimes useful when you're doing lots of cancellation to do the different cancellations and different designs so you can see like what's canceling with who. Neato. So, with the remaining time, there's not much. I've got like 40 seconds. Maybe I'll flip over and see the next couple of pages of this packet are all devoted to why are the logarithm laws true. We'll use them all over the place in this class. It's just like a black box. We'll believe that they are true. But they're not true for any super deep reason. They're true because you have exponential laws. So here's what I'll have you do. Go through this document. Read through the instructions. Try to parse out what ideas this is trying to get you to follow. And then come talk to me, get your extra credit. If you're having trouble getting started, but you want to like read through it, come by my office. We'll have a conversation and get you started. Because you're allowed to ask me about any extra credit at any time. I guess after the semester would be true. Cool. All right. As people pack up, remember that there is this talk that I sent you an email about on Friday tomorrow at 3 p.m. in Hibbard 100. The location is in the email. It's in this building. Cool. Okay. I'm bad at saying goodbye. See y'all tomorrow.